Armed with this knowledge, let's now look at a more recent paper called Superscalar Sample Sort. And this is based on sample sort, but our motivation is not multiprocessing. Our motivation is a single modern processor. The main step that we're going to concern ourselves with is how do you distribute the elements into the buckets. So we're going to say we have our array and we already have our sorted array of splitters. And the task that we will now consider is we want to distribute the entire array into the correct cardinality of p plus 1 buckets. Because if we have p splitters, then we get p plus 1 buckets. And so the algorithm is going to be, we're going to loop over A, and then for each element, we do a binary search on P to find the appropriate bucket, right? It's sorted. We can do this. It's efficient. It's pretty nice because this means that log of P time per element is enough, and this is a reasonable amount of time to be spending on that. However, thinking back to our dislike of controlled dependencies, this is actually also still log of P branches. That's going to be a lot of pipeline flushes again. And so we get back to this idea, could this be data dependency rather than control dependency? In order to set us up to do that, I'm going to make a small change that doesn't do anything, which is I'm going to say it's not a sorted array. I'm going to say it's a binary search tree. And rather than binary searching on the sorted list, we're going to search the binary search tree. That doesn't really change anything, but it'll be nicer to think about because how are we going to store this tree? And our goal is going to be branchless bucket selection. What I want you to remember is that there was this binary heap data structure where we also have a binary tree that we want to store in contiguous memory. And then there's this fun trick where we put the root at index 1. And then for a node I, the left child is a 2i and the right child is a 2i plus 1. So the root is 1, left child of the root is 2, right child of the root is 3, left child of 2 is 4, right child is 5. Left child of 3 is 6, right child is 7, etc. So if we draw this as a tree, then we always multiply by 2 going left, and we multiply by 2 then add 1 going to the right. Let's put some values in this tree. Black numbers are still the indices. So let's consider what happens if we traverse this tree. What does that look like? Well, we always start at index 1, and then we want to compare with that element. If we are smaller, we go to the left, and if we are larger, we go to the right. So what happens to the index that we should look at? Well, it always doubles, and then if we are larger, we add 1. 115 is larger than 42, so we do add the 1, and we go to index 3. Then we compare 115 to 201. We always double the index, but this time we were smaller, so we don't add the 1. We go to index 6, we compare to 90, we are larger, so we double the index and we add the 1. After we've done the entire tree, then we end up with index 13, but this is a weird numbering, so we subtract 8, right? Because we had our 1 indexed tree of size 7, so we subtract 8, and the element 115 should go into bucket 5. And the thing to notice here is that if we have a processor that can do a predicated increment, and if we can convince our compiler to use it, then this algorithm has no control dependencies. Let's see what happens. Let's implement it. And in this example, I'm going to do it specifically to split it into 16 buckets. I say we're going to get given a pointer to this representation of the tree, where at index 1, I have the root of the tree, and I get given an element x, and I want to know, based on these splitters given in P, which bucket should the element x go into. And I'm just going to write the thing that we had before, right? So I have I started in index 1, which is the root, and then while I'm still inside the tree, what I do is, let's quickly grab the pivot from index I, and then I definitely double I, which means going to one of my children. So this is the left child, and then if I'm larger or equal the pivot, then actually I increment I go to the right child. At the end, I subtract 16 this time, not 8. And now the big question is, will the compiler have a conditional jump here for this if, or will it do some kind of predication? Now, I might try to entice the compiler by writing it like this. I plus equals the Boolean of whether x larger equal p. This kind of smells more like a predicated increment than the if before. But when I tried it, the compiler produced the same code either way. It does the predication. And what it looks like is this. So on the left, I have the disassembly. On the right, I have my annotations. First, it's going to put 1 in the A register. And it's going to use the A register as kind of our index. And then C is going to be the conditional. So it's going to be the 0 or the 1 that we want to add or not. So it's going to say, for now, let's say 0. Now I compare my value x, which it put in SI. I'm going to compare it to this array lookup where our DI is the start of P, and then I is the index, integers are 8 bytes. And then here we have it, based on this previous comparison that just happened, put into the C register the greater equal flag. So that this puts a 1 if this comparison was greater or equal, and it puts a 0 if it was not. Don't worry about why we just set it to 0 and then we seem to set it here as well. There are details. Don't worry about it. The next thing we're going to do is we're going to say I gets 2i plus c. There's this instruction that allows it to do the addition and the multiplication in one instruction. And now we need to do the control for the while loop. So we compare I to 16. And then if it's less, then we're going to jump back to the top of the loop. When it's not, then we fall out, and then we subtract 16 and we return. So I think this makes a reasonable amount of sense. What we see is that there are still control dependencies in this code, but it's only the while loop. Comparison between the element and the pivot has now become a data dependency from this comparison to this set from the flag to this addition. So that's nice. We might say that, okay, this while loop conditional jump is reasonably predictable. We take it most of the time. We take it 3 times out of 4. But let's see if we can do a little bit more with that. So could we reduce the loop overhead of this while loop? Well, we know that this loop is going to happen 4 times, right? So what I could do is I could take this code and just write it 4 times, and then I don't have to check this. But we can actually also get the compiler to realize this. It's not quite up to the task of realizing that this loop necessarily happens 4 times. But if we write this for loop, then, well, initially you might think this is more work, right? Because I have to increment this j. I have this extra variable, I'm doing these increments. So that sounds like more work. But actually writing it like this, the compiler is, at least in this case, is able to figure out, oh, okay, this loop definitely happens exactly 4 times. So then let's look at the code that it generates. So what it did now is a thing that's called loop unrolling. What I highlighted for you in blue over here is the 4 comparisons that it does. It compares to the first element in the array, which is 8 bytes after P. It starts using the A register as the index. So then you get start of the array plus 8 bytes times the index, 8 times the index, 8 times the index. And then what you see it doing is it does a comparison and it grabs the status flag for greater or equal. Here, for some reason, it does the comparison the other way around. It doesn't matter. It can do that. And then it grabs the less equal flag and it grabs the greater equal flag here and grabs the greater equal flag here. So basically what we're saying here, just at a quick glance, is it's doing the 4 comparisons that we expect it to do, and it does it based on this A register where it's going to count the index. So the first time what it does is it has the condition flag in A, and then it's going to add 2. Well, yes, because the index starts out as 1, and then if you double it, it's 2, and then the A register is either 0 or 1. So this actually effectively does the first step, and then the next time, the third time, double A, and you add the condition flag. And then the final time it has an extra trick up its sleeve, because this LEA instruction can also inline add another constant. So it pulled the minus 16 from the end into this instruction. This is now the code that it generates from this from this code, which has a for loop and an if, But then what it ends up generating over here is this straight line code with no control dependencies at all. A thing that could be criticized about this code is that it is longer, so it also takes more memory, just in terms of how large the code is, which, if it gets extreme, could be a problem. But in this case, is probably a win. The compiler is pretty good at making that judgment, and in this case, it did judge that it would like to unroll this loop, which I think is pretty cool. How, let's say, far away the generated code is from how you might imagine your code runs if you just look at these for loops and these ifs. And this is a real performance win that your compiler is able to do for you automatically if you give it code that has this kind of shape. It wouldn't be able to do something like this if you just type out quicksort, right? So by making the code have a shape that is close to something that you might do like this, then your compiler is able to do it for you. But again, if it's important to you, you do have to check. Like this happened at 03 for me, and it did not happen at 02. So you do have to be careful. The compilers are infinitely complex. So if you want to rely on it doing a particular thing, you always do have to check or have different ways to force it to do the thing that you want it to. But we're very deep in the weeds now on very specific things that your processor does or might not do. And I don't want to make this video too long, but we kind of got sidetracked there. So let's quickly wrap up superscalar sample sort. Why were we even doing this? This was very nitty-gritty code for finding out what bucket does a particular element go into. What was going on around that is that we have our array, we have our set of pivots, and we want to put the elements in the correct bucket. To repeat, quicksort has this very efficient in-place partition, and superscalar sample sort gives up being in place. We're going to ping pong between two arrays of size n. We're on one side, and then we're going to put the buckets on the other side, and then we have the buckets, and then if we recurse, we're going to come back to the first one, etc. So I have my array A, I have my set of splitters, which here I've represented as a sorted list, but in our implementation would be a search tree. What we now want to do, we want to group the elements of A into their buckets. And one way that you could do that is have a growing vector for each of your buckets, but this turns into a lot of memory management, right? This is overhead that we don't really want. So what they're going to do is we're going to do two passes over A. And in the first pass, for every element, we're going to figure out, okay, which bucket does it belong to? And we're just going to count. We're going to have an array. You can put it in the smart place, but you can think about that yourself. We're going to have an array, and we're just going to count how many elements are going to end up in each bucket. So just calculate the bucket ID, increment the counter. And then if we have these bucket populations, then we can easily put indices into an n-sized array where those buckets would start. So then I do this in one pass over the array, and then I do another pass over the array. And I put elements in the correct bin. So I look at first element, it's a 1. I do the traversal of the tree. I see it has to go into bin 0. So I put it in bin 0. I update this index. So the next time I'm going to insert something into bucket 0, I'm going to put it here. I look at the 6. That's bucket 2. So I put it over there, and I increment this. And then I put everything in its correct place immediately. So what I have to do is I have to do two passes, but they are sequential passes, so they're not terrible for cache. And in this way, I've basically solved all of my memory management problems, because having done these counts the first time, I then immediately know for every element where it would have to go. You have to think a little bit about how you implement this for real, but that's a nice puzzle that you can do on your own. And this is really all I wanted to say about superscalar sample sort. There are, of course, experiments in the paper. I encourage you to look at those, but that's not really something I want to do in this video. I just wanted to mostly tell you about how bad branches are for a deeply pipelined processor, but that this is not the end of the world, and this is actually something that you can be smart about, and that non-trivial algorithms can be made branchless in this sense, in terms of control dependencies. And I think this is really fun. That's one thing I wanted to show you with this video. And the other one is I wanted to give you a little bit of a feeling. And I hope I succeeded with that. Maybe I just made you scared. But the feeling I wanted to give you is that with a little bit of puzzling, you can read disassembly. There's this website, I mentioned it before, Compiler Explorer at godbolt.org. You can just read it, and you're going to get better at it. But it has documentation and everything, and that's how I got the disassembly that I showed you in this video. And it's actually kind of fun, and it's a good skill to have. I think you shouldn't be scared of it, and that's maybe one of the things that I hope that you take away from this.